Now, linear approximations, this is a method to simplify a function and approximate values really close to x equals c. Some value c, wherever you're looking at, because we're going to have a focus point. We're going to be focusing in at x equals c. And once we focus in at x equals c, we can use linear approximation to figure out values. Like if c was 8, we can figure out 8.05 without putting it into a function that's really, really crazy. Now here's an example. The function f of x is equal to the cube root of x. And the question that you'll see is determine the linear approximation for f of x at x equal to 8. Then use it to approximate the value of the cube root of 8.05 and the cube root of 25. Alright, like I said before, this is a step-by-step process. You follow step 1 to step 2 to step 3 to step 4 to step 5 to step 6. Well, there aren't 6, but there's 4. Alright, first thing you do, find f prime of x. Now, if we think of f of x as x to the 1/3 power, we're going to get 1/3 times x to the negative 2/3 power, which is 1/3 times. The root is 3, and the power is 2. You could keep it as the exponent if you want. Not really. This might be easier to deal with if you know that the number you're dealing with is a cube root. Now, second thing we have to do, find f of 8 and find f prime of 8. So if I take f of 8, that's the cube root of 8, which is what? 2. If I take f prime of 8, this is going to be 1/3 times the cube root of 8 squared. Do you know what the cube root of 64 is? 4. So it's 1 over 3 times 4, which is 1 over 12. So if I'm doing linear approximation, what do you think the equation is going to be? Linear is a line, right? And so for step 3, we'll call this L of x, because we're very creative in the mathematical world. L for linear approximation. Our creativity is all about making sure that we can look at this and say, well, L probably stands for linear. Logical creativity, that's what I call it. This is going to be f prime of x times x minus c plus f of c. From here, from this equation that we got here, my c was equal to 8, my f of c was equal to 2. And this is equal to f prime at c. So do I have all 3 parts that I need to make my line? All right. Say that again? It doesn't really matter as long as you know that you're working at a point. Just remember, you're always working at a single point in this case. But you're right, I should be consistent. Hey, it's the first day back. I barely got up this morning. Which looks like some of you have barely gotten up. That's okay, though. Alright, so L of x, my linear approximation, f prime of c is 1/12, isn't it? So 1 over 12. Then I'll get x minus, 8? Plus 2. Simplify it one more time, well, 2 more times. That's 1/12 times x minus 8/12, which would be, which would be 2/3. Plus, what's 2? That's 6/3, isn't it? Since we're stuck with thirds, because I'm gonna have 2/3 plus negative 2/3 plus 2. But if I change it all into fractions, I can just add the fractions really quickly, like. Alright, so now I have my linear approximation. Yeah, but then you have to do L of 8.05, and because the question said find out the linear approximation of 8.05 and 25. So now this line is going to give us an approximation of the cube root of x, which is nice. So I need L of 8.5 and L of 25. Where? That's not the case, because what we're going to do is we're going to say this is like x sub 1 and this is like x sub 2. So now that we've created this equation, this L of x is going to be approximately the third root of x. That's the whole idea of linear approximation, is we've created a line that's going to give us something that's really close to what the actual answer is. So instead of trying to take the cube root of 8.05, we can plug it into a linear equation, which just has one thing of multiplication and one thing of addition or subtraction, and then we're done. And now granted, it becomes a calculator problem at this point. So we need to put it in a calculator. 1/12 times 8.05 plus 4/3. And I got 2.00417. This is actually 66666 repeating. That's what we get there. Now, if you plugged in L of 25, we get 3.41666667, or 6 repeating, 7, that type of thing. But here's a question for you. What's the actual cube root of 8.05? Isn't it 2.00? $415,802. So basically, it was 2.00416, and we got 417. That's pretty close, isn't it? Because you're going 1, 2, 3, 4, 5 decimal places. So that's a minuscule amount of difference there. Now this is 2.92401174. Now, is there a big difference here? Small difference. Here, big difference. No. Well, that's the question, is why are we going to get a bigger difference with using 25 than 8.05? Here's a question for you. What number did we start with?
8.
Alright, we started with 8. So if we looked at the number line, we went 8, and then we went over here, 8.05, and then we went way over here for 25. Which one gave us the better result? So this gave us a great result. This gave us something that was not so great. So why do you think that's the case? Yeah, that comes down to it. 8.05 is a lot closer to 8 than 25 is. And as a matter of fact, the farther you get away, the farther that you get away from the number that you're actually dealing with, the more error comes into play. Is there some error here? Absolutely, but it's really, really tiny. There's a tiny amount of error, very tiny. But the error grows the farther from C that you get. So the whole idea behind linear approximation is we want to be able to simplify a function down, but the use of that function is always going to be, we want to make sure that we're sticking close to C. And if we don't stick close to C, we're going to have too much error come into play, and then the approximation is really going to fail us. And we don't want the approximation to fail us, so what we want to do is make sure that we keep things pretty close to the number that we're actually dealing with.